If you haven't already watched the video looking at the physics of an inclined plane and a leg press, watch that one before starting this one, because now we're going to start talking about friction and its role in the work that we have to do coming down here. I've kept everything the same as in the previous leg press. We've got 100 kilos, we've got gravity doing its gravity thing, we've got a 30-degree incline, we've got a component of force that is parallel to the slope, a component of force that is perpendicular that's pushing into it, a normal force pushing back up that is equal to the inverse of mg perpendicular, and then we have a certain amount that's going to be fighting back against the amount that's coming down the slope, a certain amount of force that is kicking in this direction that we're going to call F sub F, which is the force of friction. So what is the force of friction? We're going to need to do our SOHCAHTOA calculations again to go, okay, well, how much is mg perpendicular equal to, and how much is mg parallel equal to? And so they're both going to be equal to mg, because that is the origin of their force, and then they're going to be related to either the sine or the cosine of the angle. Perpendicular is right adjacent, so adjacent to theta. This angle is the same as this angle, so he is this force coming down here. So mg perpendicular is mg cosine, and we said that's 30 degrees, so cosine of 30 degrees. And mg parallel, as we covered before, was the sine of 30 degrees. Now we know that mg perpendicular is also equal to the inverse of n. Whatever that number is, that's the amount that's also pushing back up, because it's not coming through the leg press. But it is this force pushing down, pressing something into the surface of it, that allows us the capacity for friction. You'll notice that friction plays less of a role when you're bolt upright against something. It's way easier to slide down. And that's because this force gets relatively larger relative to it, and the force pressing us into the surface decreases as well. So our frictional force is going to be equal to N, or which is really equal to mg perpendicular, times a coefficient. And so the coefficient of friction, let's write a coefficient of friction, is written like this, mu, which is like a U with a bigger kick off the side, and it has two types, static and kinetic. Static is always bigger than kinetic. And you know that. If you try and move something along, it's harder to get it going. Then once it starts going, there's less friction fighting it and it'll keep moving. So static is larger than kinetic, but it means we have two things, US and mu K, kinetic, static and kinetic. So this force here is actually equal to, we can remove this question mark now, the normative force, which we're just going to call mg perpendicular, times the coefficient that we happen to be dealing with. We're static right now, so let's say we have a coefficient. And how much is our coefficient going to be equal to? Well, let's say that our static coefficient is equal to 0.4 and our kinetic one is equal to 0.2. You can go and look up tables of those. If you put coefficient of friction into Google, you can find a whole laundry list of different materials on different materials. They have to be empirically calculated. They're not the same for two different things, because even if I have two objects, if one of them gets a bit more moisture on than the other, if it's something like wood, you've got different grain alignments and arrangements. So it's never perfect and never precise. We can never exactly know what the kinetic coefficient is going to be. We can get close. And if we're using something like oiled ball bearings, that's going to be really different than if we're using rusty iron on rusty iron. Okay, so F friction is equal to mg perpendicular, which is itself equal to mg cosine of the angle, times whatever that coefficient is. So let's start figuring that guy out. Calculator time. Let's go, first of all, mg perpendicular is equal to mg cosine of 30, so we've got 100 kilos times 9.8 times cosine of 30, and this guy is equal to 848 newtons. Okay, and we before went, and that itself is equal to about 86.6 kilos. That's the amount that is pressing down here into the slope. N is equal to the opposite of that. So we're going to need to times this number by our static coefficient. So we've got 848 newtons times 0.4, which is itself, let me just get that back to that guy, times 0.4. And we've got this force here, 339.5 newtons. And this force now is the frictional force. It is equal to mg perpendicular times the static coefficient. So the static coefficient is that number right there. And again, if we wanted to put that in terms of kilos, so that you kind of made sense of it, it's equal to about 34.6 kilos. Well, how much was mg parallel equal to? Because that's the force fighting it. So mg parallel was mg sine of 30. So mg parallel was equal to 100 times 9.8 times sine of 30. And he himself was equal to 490 newtons. So the question is 490 bigger than 339.5? Yes. How much bigger is it? It is 150 newtons more. So if we go 490 minus 339.5, we are left with 150.5 newtons, or, because we're talking about these things in kilos, 15 kilos coming down the slope. If that was our kinetic coefficient, we'd only have to deal with 15 kilos to press back at that. Except we had a static and a kinetic. The static is, does it start moving? Because if it can't overcome that static coefficient, if I took that coefficient to 0.6, so let's go back to that and go, okay, we've got 848 times 0.6, that would give me 508. Is 508 bigger than 490? Yes, that object wouldn't move with a with a static coefficient of 0.6. But it is moving. And now it's moving, we have to use the kinetic version of it instead. So now we have 848 newtons times 0.2. Because now, so let's say over here, it moves. Written small down the corner. Now we have mg parallel is still equal to 490. But can 848 times 0.2 is equal, this guy is equal to 100, I'm just going to round that up to 170 newtons. So 490 minus 170, this guy is, so minus 170 equals 320. So we have 320 newtons we're dealing with down the slope, or divide by 9.8 again. 30, I'm going to round this up, 33 kilos. So once it started moving, now we're dealing with 33 kilos. So of the 100 kilos that was on the slope, well, I only had to deal with 33 kilos to stop it coming this way. Now, here's a fun part, and I've run out of room on the board to do this, so we'll just talk about it conceptually. When I start pushing back up the slope, what's going to happen? That frictional force now fights me. So this number, first off the static one and then the kinetic one, would be added to that guy. They would be added to the amount coming down the slope, because that's still trying to come down the slope. But now we have this. So if I had 490 plus 339.5, I've got 829 newtons divided by 9.8. I've got 85 kilos. So isn't that funny? I've got 15 kilos when it comes down, but when I push it back up, if that's the frictional coefficient in a static position, now I'm dealing with 85 kilos. 15 kilos when I'm going with it, 85 kilos when I'm fighting against it. Now we're only dealing with that static guy instead, so now we're going to have to take our 490 and add on 170. So now I've got 660. And I'm going to divide that by 9.8. And once I get it moving back again, instead of 85 kilos, now I've got 67 kilos. But either way, that's a difference from having to deal with 33 kilos as it starts traveling down to 70 kilos near enough as it goes back up. Now, you'll see with plenty of kinetic and static coefficients that they go down if they've been well oiled to things like 0.001. Well, you can kind of ignore that if that's the case for the concerns that we have. But it's interesting to note how big a role friction can play in what we're dealing with here.